And let's start with some classical facts. So there is one line through two generally chosen points in the plane, and there is 1 degree 2 genus 0 conic through 5 points in the plane, and there are 12 genus 0 degree 3 curves through 8 points in the plane, and there are 620 degree 4 genus 0 through 11 points in the plane. This goes on, and these numbers are computed through 3D minus 1 points. You can do this in P3, and PN and the projective complex varieties. But I'll do just a few more because I like them. So there are 27 degree 3 curves through 6. So 2 times D in P3. We can do, we don't have to do through points, we can do through meeting other sorts of varieties. So there's a whole family with 2D points, and then there are 2 lines meeting 4 lines in space. If you believe that you could move these lines and not change your count, then you take 4 lines in the room and you decide to degenerate 2 of them so they meet at a point, and degenerate the other 2 of them so they meet at the point. And then it's true that the count of the lines meeting those 4 lines is the same. And how many lines is that? You can visibly see it. There's 1 line between the 2 cross points, and then each of those 2 together, they lie in a plane. And so those 2 planes intersect in another line, and there you have it. Those are the 2 lines. And this fits in an infinite family. There are 2n minus 2 factorial over n factorial, n minus 1 factorial lines meeting 2n minus 2 codimension 2 hyperplanes in Pn. And this is all over the complex numbers. Over the real numbers, the number of such curves varies. It depends on where you choose your points to be. So there can be 8, 10, or 12 real curves through 8 real points. And if we want to set up these counts, we can do it cohomologically. So these are all example of Gromov-Witten invariants. So we're interested in all curves satisfying some conditions. So let's express those conditions with cohomology. Let's take X smooth projective over C. And then there's a Kontsevich moduli space consisting of all of those curves of some sort of degree. So we'll take a degree, like degree 3, degree 4 in each 2 XC. It could be with Q coefficients. You could do with Z coefficients too in certain ways. And then there's a moduli space of all the curves of that degree in X. And in order to get nice invariant counts, we want this to be compact. There's a funny quote about maybe it's due to Vistally, I can't remember, about working with non-compact moduli spaces is like trying to count your change when you have a hole in your pocket. So they make a compactified moduli stack consisting of, in fact, you can even do genus G, of maps from a curve to X, and C, it doesn't have to be smooth. We're going to allow it to bubble off and pick up more components to make the space compact, but it has to be nodal and arithmetic genus G. And this has to be stable in the sense that the automorphisms of the map are finite. And we want it to be degree B, so we want the push forward of a fundamental class of B, of C, the curve C, to be in the class beta. And then we want to make sure that there's certain incidence conditions happening. So we're going to record endpoints. So in P1, it's pairs of a map of degree B, and P1 through Pn, where the Pi are smooth points of C. And then we'd like to count how many curves are meeting some lines or going through some points. So we can take cycles representing those lines. So if we have gamma I cycle of some dimension Li on X, it represents some cohomology class like that of a line. We can take the Poincare dual of, let's actually say it's dimension X minus Li, and then we'll take the Poincare dual of that and view it in cohomology of degree Li on X, and the number of genus G degree beta curves on X meeting our cycles is then the push forward from the moduli space, or the integral from the compactified moduli space, and you have to make sure that's well defined. This is some sort of integral over the moduli space of the pullback of these cycles under evaluation maps. So we also have evaluation maps M bar Gn X beta X that takes the data UCX P1 Pn, and it takes the image of Pi. This goes to U of Pi. So we want to require that, let's say, the ith point meets the ith cycle. So we pull back the Poincare dual of gamma of I, and we take the cup product of all of these. So those are conditions on the curve. It's got to meet those, and then we push it forward, and that's the number of such curves. So we'll call this nx beta of let's call these sigma I of sigma 1 sigma n, and those are our Gromov-Witten invariants. Okay.
Sorry, is B like is H2X isomorphic to Z, or how?
No, it's just in the case of P2 and P3. So then the degree it depends how you define degree, but I mean, it's the push forward of the fundamental class in Chow. And I mean, you could make a moduli stack with other conditions, push forward maybe in Chow Vit and make yourself these things come, they're Deligne-Mumford stacks, and Barron and Fitecki proved their Deligne-Mumford stacks, and they have lots of tools available to think about them. Okay, so our goal, as yesterday, is to record arithmetic information about these curves going through these conditions. Information about the curves making up this finite number of curves. If we've put this so that it's in, this might be in H0 of the point, if the sum of these, so when the sum of the Li is the virtual dimension of the moduli stack. And if these are going to be Q valued because you've got stacky points and you're taking H0 and Q to make the push forward more standard, to have better tools to talk about what a push forward is. So this is some rational number about the curves. So this would be Q. Making up the finite rational number, because you divide it by automorphisms. That's the way the push forward is going to work, of curves satisfying these conditions, passing through the cycles. Through gamma n. And the tool that we'd like to use is to use cohomology theories that can pick up arithmetic over bases, over rings and fields. So we want to use SH of the base. So the stable A1 homotopy category of Morel and Blavatsky, or we can use stacky versions due to Khan and Ravi and Chowdhury. So there's a kind of least extended theory for stacks. So we could take some sort of arbitrary base. We could let this be a stack. And for the global quotient stacks, this is in work of Hoywa and Chowdhury and Khan and Khan-Ravi. And there's a version for scalloped stacks that's less formal, and they have versions to work with this. There are other ways to talk about singularities. So let me advertise the log motives of Binda Ostfair. And the non-A1 invariant version of A1 homotopy theory, or the cohomology theory for these schemes, not required to be A1 invariant of Anala, Hoywa, Iwasa, and Longka Tang, who in particular defines push forwards. If you got very lucky and that was a smooth, proper scheme, then you've already got push forwards due to Longka Tang's Giesen paper on Giesen maps. So our heuristic is that with a sufficiently good cohomology theory E in our stable homotopy category, understanding of the geometry. Let's see. And geometry of the moduli stack, we can define these n, x, theta, sigma with exactly the same definition, where we now have cohomology in E value cohomology, but we can, let's say we've done the work to define some push forward of the pullback and we'd like it to land in E0 of the base K. We're successful in doing that in some cases where E0 is the Grothendieck-Witt group we discussed yesterday. So example, E0 of K, the Grothendieck-Witt group of K. Again, this is the group completion of isomorphism classes. Symmetric, non-degenerate bilinear forms. And our answers are going to be very computable. There'll be little numbers and brackets instead of little numbers. And so the little number and bracket notation is that A bracket denotes the class in the Grothendieck-Witt group of the one-dimensional bilinear form from K cross K to K. And for it to be non-degenerate, we want A to be a unit. It could be any ring for these to be in there. And bracket A sends XY to AXY. And then in GW of K, if you have an embedding of K into R, then we'll get compatibility with enumerative results over C and over R by taking the rank and the signature. So given this and R, we have a compatibility between our counts. So if we take the degree of a map from Pn over Pn minus 1, and it's in GW of K, then if we take the rank, we'll get the degree of the C points. And if we take the signature, we'll get the degree of the R points. Okay. Let me define, so while we're talking about GW of K, I'd like to define the I'd like to define some binomial coefficients we talked about yesterday. So by Galois theory, étale extensions, finite étale extensions of K correspond to sets. And the set of subsets of a given set of a size is a binomial coefficient. So let's talk about twisted binomial coefficients. And GW of K, and this is with A1-homotopy, Cheng-Yao Chen. So let's give ourselves, let's say K a field, and on smooth schemes over K, the Grothendieck-Witt groups, if we sheafify them for the Nisnevich topology, make an unramified sheaf. So let's let GW with an underline be the sheaf of abelian groups, which is the sheafification which sends some K algebra R to the group completion of the non-degenerate symmetric bilinear forms over R. And then for a finite étale Y over X, we can define Y choose J for some integer J. So if we take X geometrically connected, and little x a geometric point of X, we have a fiber functor corresponding to X from finite étale schemes over X to sets with an action of the étale fundamental group. So which takes Y over X goes to the fiber of the fiber of Y over X. This goes to Y cross over capital X with little x, which is just a set because it's a set of geometric points lying over little x. Set of points. Minus 1 of X. So then if we want to choose J of them, we can take the subsets. So let and this is an equivalence. So also if we had a pi1 étale XX set, if we have a set with an action of the fundamental group, we also get a finite étale algebra, I mean, a finite étale X scheme. So let's let the set Y over X choose J be equal to the set of subsets of the fiber of Y over X of size j. This set of subsets has a Galois action, has a pi1 XX action because the whole set has a pi1 tall x action. And so the definition of the binomial coefficient in the Grothendieck Witt group of x is then you take the trace form of the corresponding finite étale x scheme. So so this is going to correspond to a finite étale x scheme. And it has a trace form, finite étale x scheme, c over x, and then there's a trace form going from f star of O of c cross f star O of z, since there's always a map from f star O of z, tensor f star O of z to f star O of z. Since f is étale, this is the same as the determinant of the cotangent complex. A cotangent complex is trivial. So this is also f star of omega, of f, the determinant of the cotangent complex. And then Serre duality says that there's a trace, the sum of all the Galois conjugates down to O of x. And this is a bilinear, symmetric, non-degenerate bilinear form. So it has a class in the Grothendieck Witt group of x. So we'll define y over x choose j in the Grothendieck Witt group of x to be the class of that trace form. So definition for y finite étale over x and j a positive integer 0, 1, a non-negative integer, let y over x choose j in the Grothendieck Witt group of x to be a trace form of the finite étale x scheme corresponding to the set, well, the set y over x choose j. And so we saw Pascal's triangle on the board yesterday. For a finite field, there's one extension of every degree, so it really fits into a little triangle. And there are lots of non-trivial discriminant terms all over the place in that triangle. You can tell exactly where they are for finite fields, but it's not like it's not a boring answer. It has to do with like digits, mod, base 2, and things like that. So we're going to need twists. So if y over x is degree 2j, and we're choosing j, then we can also swap a subset with its complement. And that's going to turn up in calculations. Let's let characteristic of k not be equal to 2. And then if we take y over x, finite étale of degree 2j for some integer j equals 0, 1, etc. And we take a given degree 2 extension, some finite étale degree 2 extension, but that's always going to be the square root of something. So if you don't mind, I'll just denote the fixed. It's any finite étale degree 2 extension, but let's denote it by square root of d. Degree 2, then we're going to let twisted binomial coefficient, so let y over x twisted by the square root of d, or twisted by x adjoin the square root of d, choose j, be the trace form. So in GW of x, the trace form of the finite étale algebra, of the finite étale X scheme, where so we have so with pi1 action, so we have that pi1 surjects onto the Galois group of x adjoin the square root of d over x. So pi1 tall xx maps to the Galois group of x square root of d over x. And then it also maps to itself by the identity map. And then the Galois group for this degree 2 extension, we're not in characteristic 2. This is just canonically isomorphic to the cyclic group on 2 elements. X. But we have 2 commuting actions, one of the cyclic group on 2 elements and one of pi1x on this set of subsets. So this then acts this acts on the set of y, x, choose j, where C2 acts by taking a subset to its complement. So where C2 acts by taking a subset of size j to complement. And that commutes with any action on a set. So that's an action on the product. So that pulls back to a different action of pi1 étale. So that's a different étale X scheme. And so that's a twist of those binomial coefficients. Again, they still have the same ranks from Pascal's triangle. They'll have rank the degree of y over x choose j. But they're carrying information about sort of which embeddings into the algebraic closure you are choosing. So we're going to be choosing from various field extensions, and we'll keep track of the choices of the field extensions. Okay. So these can be used to calculate some Gromov-Witten invariants. And the ones that we've got really good definitions for Del Pezzo surfaces. Then we can push forward without rationalizing, because you can get rid of singularities and sort of cut them out, and then you've cut out too much, but you can then we can put some stuff back, and then you can really push forward integrally in the Grothendieck fit. So here's the Gromov-Witten invariants that are really going to lie in the Grothendieck fit group of K. So it's a theorem and a definition, joint with Jesse Pass and Mark Levine and Jake Solomon. So let's let K be a perfect field of characteristic not 2 or 3. And for simplicity, let's, well, actually, okay, for simplicity, let's let X be a Del Pezzo surface. So that's smooth projective over K, and its anti-canonical bundle is ample. We can really do this in some cases when the degree is greater than or equal to 2, but it's easier to state when the degree of the Del Pezzo, which is the self-intersection, is the class in pic of X of the determinant of the canonical bundle. And let's say that this is bigger than or equal to 4. Let's assume that X is A1 connected. So this includes examples like blowups of P2, rational. There's a theorem of Arvind Ashok and Fabian Morel that if you're K rational, rational over K, and a smooth projective surface, then you're A1 connected. So that includes things like cubic surfaces that have 2 rational lines that don't meet, or a pair of conjugate lines over a degree 2 extension. So there are a lot of A1 connected Del Pezzo surfaces. We're going to pick a degree that's like in Chow 1, but that's also pick because we're on the surface. So let beta be our degree. It's an pick of X. And then we're going to just go through points. So let sigma equal L1 through LR, a list of field extensions. We're going to pick generically points, or at least in some virtual way. Sometimes there aren't Li points on a given interesting Del Pezzo surface, even if it's A1 connected. But we're going to run, but a lot of the time, first of all, on blowups of P2, you pick generic points whose coordinates are defined over L1 and LR, and you count in some with some weight the curves of degree B going through them. So this is a list of field extensions of K, serving as the fields of definitions of the points we're running the curves through, and there has to be the right number of them to get a finite count. So with the sum as I equals 1 to R of Li over K equals the right number for the dimension of the moduli stack is minus Kx beta minus 1. And the conclusion is then there is a well-defined X beta sigma in GW of K. So we have this Gromov-Witten invariant. And in fact, there's an enumerative interpretation to this, but let's skip it. So let's compute some of these with our binomial coefficients. It was useful when we counted lines through 4 lines in space to move those lines until we could count better. And so that's about deformation invariance of Gromov-Witten invariance. And sometimes when we reach the boundary of this space of Del Pezzo surfaces, it's no longer deformation invariant. We're going to cross some kind of wall in our space of Del Pezzo surfaces. And then we'll see how the Gromov-Witten invariants change. So we're going to change the arithmetic structure by a surgery and compute the change in Gromov-Witten invariance. Okay. Structure by a surgery and compute change and x theta sigma. And this is joint with A1-Brugler. Surgery here doesn't literally mean the topological kind, although on real points, it literally is a topological surgery. But surgery here is going to mean blowing up a node on a one-dimensional family of Del Pezzos. Where we're going to have a family of Del Pezzos that acquires a -2 curve. If you blow down the -2 curve, you get some sort of node, and we're going to start blowing up the node in different ways, and that'll produce that'll really produce surgeries of the real points. So since we're going to blow up a node, when you have a node and you blow up, and you're going to get some sort of quadric. And because of our dimensions, we're quadrics in P3. So let's look at the quadrics in P3. So let's draw them. Quadrics in P3 of R. Let's have our coordinates be X, Y, Z, and T. And we'll have, in the middle, we'll have our cone, Z squared equals X squared plus Y squared. So there's a cone. Over here, let's have Z squared minus X squared minus Y squared plus T squared, and that's a P1 cross P1. And over here, let's do, instead of plus T squared, let's do minus T squared. So Z squared minus X squared minus Y squared minus T squared. And then this looks like it's real points. We've cut out an S1 cross an interval here, and we've glued in an S0 cross a 2 disk. So when we change the coefficient of the T squared, what's happening to a quadric is you're changing the result by a topological surgery. So what we're going to do is glue in a quadric along a -2 curve on a smooth projective surface that would have been a Del Pezzo if it didn't have that -2 curve. So let's glue in a quadratic discriminant D and K star over K star squared along a -2 curve in what's called a weak del Pezzo. E.g., for example, a weak del Pezzo is if you blow up 3 points on a line in P2, and you could twist that, or you could blow up 6 points on a conic. In P2, and then this is just algebraic. So the non-heuristic definition is you take a family. So let's define a one-nodal Lefschetz vibration is a family X over spec K, the power series ring in T, which is smooth and projective, and has a general fiber over K over the Laurent series with general fiber a del Pezzo surface and a single node over K on the special fiber, which is so the node will be rational, and it's rational, and nodes over non-algebraically closed fields, they have interesting quadratic forms associated to them. So let's write down that form. So X naught P, its completed local ring, will look like K of XY. Actually, the special fiber would be some quadratic Q plus T. So we know what kind of node it is on the special fiber. It's a rational node, and it's associated to a degree 2 homogeneous Q. So then a D surgery. So for each D, we'd like to glue in a quadratic of discriminant D, so we can pull back by so a D surgery so D surgery X is what happens when we take X over spec K T, and we map T to T squared times D over the discriminant of the quadratic Q. and we have some pullback. This changes the kind of node so that the node all of a sudden corresponds to something with discriminant D. And then when we blow up, we've glued in a quadric of discriminant D. So D twiddle, and then the D surgery of X, sigma D is the general fiber of the blowup at the node of XD. So the special fiber, let's call this XD. So the special fiber of XD, this is a Del Pezzo surface, is a weak Del Pezzo surface. With a -2 curve. And on the special fiber, instead of gluing this in a surgery type way, you simply glue along E. You take the reducible surface, which is S twiddle, glued along E with a quadric of discriminant D. Quadric in P3 of discriminant D. So the upshot is we created a new Del Pezzo sigma D for every single D in K star over K star squared. So we hit some kind of wall in the space of Del Pezzo surfaces, and we have directions to leave from that wall corresponding to every D in K squared. K star over K star squared. So the way Gromov-Witten invariants change, so theorem. So let X be a one nodal Lefschetz vibration. But sigma D, so let D in K star over K star squared and let sigma D and sigma 1 be the D in 1 surgeries, the D surgery and 1 surgery respectively. Suppose that one of them at least is A1 connected and satisfies the same degree constraint here. So I forgot to say that let's let, oh no, there's no degree constraint with the, we put the degree constraint on the Del Pezzo surface and got rid of some other, so with at least one A1 connected. One of them connected, degree greater than 4, the degree of the Del Pezzo greater than or equal to 4. Then you can compute the Gromov-Witten invariance for any choice of the field extension. So then our genus 0 Gromov-Witten invariant for sigma D beta through some list of field extensions is the genus 0 sigma 1 degree beta through the list of field extensions plus 2 minus 2D times the sum as j greater than 0 of -1 to the j of the genus 0 Gromov-Witten invariant on the 1 surgery beta minus j times a vanishing cycle. Vanishing cycle. Of sigma. So if you take the rank, you get a formula of Abramovich and Bertram. If you take the signature, you get a formula of Bruguier and Poignot. And due to some very powerful new tools from Andreas Jaramillo Puentes and Sabrina Pauli and Jaramillo Puentes and Hannah Markwig and Felix Laurel, we have a, well, first let me say, that you can compute sigma 1 as a corresponding sum of 1 and minus 1s. Theorem Jaramillo Puentes, which is one person, and Sabrina, and let me, if you'll forgive me, then combine plus Markwig and Laurel. So if S is a toric del Pezzo, the first part is just Jaramillo Puentes and Sabrina. So if S is a toric del Pezzo, and K is a rational points, then we know, so if sigma 1 is, for example, a toric del Pezzo, then we can compute the corresponding Gromov-Witten invariance for sigma D, because we already know sigma 1. In fact, I'll just call it sigma 1. So then, and genus 0 Gromov-Witten invariant sigma 1 theta can be recovered from the real and complex Gromov-Witten invariance and open Gromov-Witten invariance for Welsh and J invariance. So we know the right-hand side, and they can also recently, so and now they can take sigma in these multi-quadratic extensions, which is very powerful. It's where it is, D2. So we can compute the left-hand side from the right. So computes left-hand side from the right. So theorem computes. We can also recover the quadratic, the case. So theorem also gives these multi-quadratic extensions. Theorem also computes the Gromov-Witten invariance N0x beta for multi-quadratic extensions by degenerating a conjugate pair of points into one point, and we're allowed to degenerate points and blow up, and making a weak del Pezzo by making two general points into the same point. So they go from an orbit, D1 and D2. But the very powerful techniques that these authors use are different. And the theorem computes the Gromov-Witten invariance for rational quadrics. KKK, all rational points for rational quadrics. And I think I'm out of time to show you to show you some examples of rational quadrics, but they're little numbers in brackets, and so they're very explicit numbers in brackets. in this paper, which is already available on the archive with all their powerful techniques, they compute lots of wonderful examples. And so there are a lot of things that are in no way of this form. They can go from things of this form to all sorts of cool numbers and brackets. And sort of what are those numbers in brackets? So actually, I will end there. Thank you very much.